All right, so here's an example of swinging the tennis ball in a circle. And we're going to find, I'm going to give you the mass, the velocity, and the length of the string. And from those, and you know gravity, of course, and from those three variables, you should be able to solve for the tension at the top, the bottom, the horizontal spot, and then we're doing that in-between spot.
Is it exact? Oh, yeah.
Yep. So what I'm going to do is I'm going to set up the equations for you, and then I'll give you the answers. I want you to try solving them on your own, and this will be a quiz that we'll take, okay? Probably tomorrow. So this will be something you can work on in class. Let's set up just the equations initially. So at the top, notice I made the vector shorter. Now this is spinning fast enough that we're beyond that like sweet spot where it's just enough speed to get over the top. So there is some tension, and the tension is going to add to the weight of the ball.
What's L?
L is the length of the string. So those two vectors will add together. So we'll have mass times gravity plus the tension at the top together produce centripetal force. When it's at the bottom, the weight of the ball is still remains the same, but instead of adding to the tension, you're going to subtract them, right? So now it'll be, and it actually should be the other way around, tension at the bottom minus mg. Why did I do it in that order? Correct. Yes, that's exactly right. The tension at the bottom is greater than the weight of the ball. If it wasn't, what would happen? If the tension was not great, if the weight was greater than the ball tension, it would, yeah, the rope would break, right? It would just fall down. So those two subtracted produce centripetal force. And then how about when it's at its horizontal spot? What impact does gravity have? There we go. So we're not even going to include it. We're just going to say, oh no, no gravity. And just set it equal to centripetal force. But the 45-degree angle one, that one gets a little tricky. So mg does act straight down.
Trig.
Yep, and you're going to have to do some trig. Now, I set it at a 45-degree angle. Yeah. So you have one vector, one component pulling away from the center of the circle, another pulling tangent to the circle. So this vector is actually in alignment with the velocity of the ball. That's what would carry it, you know. Yeah, you can do square root of, yep, you can do square root of 2, you could do sine or cosine.
Well, that's equal.
Yeah, it'll work. And it doesn't really matter because it's a 45, 45, 90, but it would be good to use the same terminology that we used for inclined planes. Remember that? This is kind of like a good triangle on an inclined plane. This.
The line that you make this mg sine and whatever the angle, is that always tangent?
Yes. Yes, it is. That's a good question. We don't care about that vector, though. Why not? Because it's tangential, and it's only the radial forces, the forces that act toward the center or away from the center of the circle, that impact centripetal force. So the tension at the 45-degree angle minus mg cosine 45 equals the centripetal force. Okay. So I'm going to give you guys some time to practice. I haven't actually solved this out yet, but I'll do so and make sure you have the answers so that you can work on that, okay? All right. We're going to do that, and then one last problem. We're going to solve a pig problem. Which is a little bit different. The ball on the string was in a vertical plane. The pig makes like a cone shape, right? So there's our flying pig. And she makes a circle, right? And let's say she's coming out at you, all right? And we will assign, let's give her an angle of 42 degrees with the ceiling, okay? And I want you to find two things: the tension in the string and her speed as she flies around. I will tell you her mass. Say she has a mass of 0.5 kilogram. And the length of the string, which is 80 centimeters long. These are actually pretty, probably fairly realistic. I think my angle might not have been quite that acute. Okay, so from the worksheet, gravity acts straight down, right? And then you should draw like a right triangle under the string. So the vertical component of the right triangle, holding her up, is equal to what? Right. So this was called TY in the homework, but I'm just going to call it T times the sine of 42 degrees. Do you see why I gave it that trig function value? Yes, exactly. So that's 42 right there. That makes sense, everybody? So it's opposite the 42-degree angle. Yeah, alternate interior. Mr. Sherman, we're very proud of you for remembering that.
That's the only thing I remember from geometry.
Okay. So if I were to actually put this into an equation, that equation would be T times the sine of 42 equals what? Yeah, good. Whoever got that in the back of the room, nice job, Shawna. Yes, you can.
That's too easy.
Mm-hmm. Yeah, you still have to find omega. So what are you going to do? I don't want to give you too much help here because I think you can probably do this next step. How are you going to find omega? How are you going to find the angular speed?
We're going to find T cosine 42 to the radius.
Yeah, you're going to deal with the cosine component, which will help you find the radius because you know the length of the string. Why would you need the radius? Trev? Right.
Would gravity be negative here?
No.
Okay.
in this because you've already assigned a direction in that equation? That's a good question. Think you can do this? With that much help? Is that not enough help, or try it right now? Try solving this for t, and then setting up the circle part. You can look back at your worksheet, and then we'll check your answers and see how you did. And go ahead and work with people sitting at